How's it going, everybody? In this video, we're going to take a look at the details behind a vSwitch. Now, in the previous video, I broke down what a vSwitch does and how port groups work and kind of, VLAN tagging versus non-VLAN tagging and things like that to kind of bring everything into perspective from a high-level overview and, a little high-level overview of how data center networking works and, Nexus 7000 versus the Nexus 2000 and how the top of row switch works with the end of row switch, how that connects your virtual machines to the rest of the network. Give you guys an idea of what data centers really look like. In this video, we're going to take a look at a little bit more detail at the vSwitch level because it's important to understand, like on the left side over here we have the virtual side and the right side over here we have the physical side. That's all well and good. Everybody makes sense, right? So what I'm going to do is I'm actually going to pull up the magnifier real quick because this is going to take a little bit of time to go through, and I think everybody will be, let's see, magnifier. It's like not working. Enter? Or did it? I don't know. I'm looking at my thing here. I'm trying to get the magnifier to pull up. Magnifier. Anywho, what we're going to do is we're going to take a look at the properties of the vSwitch just to get an idea of what it looks like and how it comes into play and the details to that. So I'm going to click on this little guy here. This little what looks to be like a word bubble, if you will. If you have like an animation, you have a person drawing out, you want to draw out their thought, like a thought bubble. So we have CDP running, and basically what this basically does is it allows me to take a look at what's going on inside of the environment. So as you can see right here, we have VLAN 1, and I really wish I had my magnifier out because I think that would help. So let me do magnifier. I'm not even sure if I'm spelling it right. So yeah, but anywho, click on here. VLAN 1 is here. It's basically forwarding traffic for all VLANs. This is the Cisco switch version it's connecting to. It's the 3550. VLAN's on port 7, the IP address of the switch, the name of the switch, so on and so forth. So some basic layer 2 capabilities, right? That's all well and great. So let's take a closer look. Let's go to the Properties tab. And as you can see here, I have multiple connections here. And basically what we have is, by default, every vSphere standard switch comes with 120 ports configured to it. This can be added up to or gone down. It really depends on what you want to do. So if you were to connect here, you could change the number of ports in increments of 24, 56, 120, 248, so on and so forth. Basically, in the not in increments of 2, but 24. I don't know why they have it set up in such blocks, but that doesn't make entirely total sense. But so you can do some things with that. So if you were to take a look at this, so this is the base connectivity. If you were to look at the way that it is set up. So right now we have the vSwitch. This is vSwitch wide. So when you click on this, you're talking about anything that's on this vSwitch. I'm going to edit the settings for the entire switch. So promiscuous mode is set to accept, which means it's going to accept traffic from other VLANs even if it isn't supposed to. By default, this is off. So what you're going to do is, if you were to click on edit and go to, so you have your properties, the number of ports, and your MTU or your maximum transmittable unit. By default, Ethernet is set to 1500. There's no, you can modify that up if you want to do jumbo frames, things like that, if you're going to be doing bigger ports or bigger faster port speeds and stuff like that. If we click on the security tab, we're going to have promiscuous mode, MAC address changes, and forged transmits. So the idea here is promiscuous mode means that anything that's coming towards the vSwitch for a particular MAC address, even if it's not destined for it. We have MAC address changes, which basically MAC address changes is going to be traffic that is leaving, going out towards the switch. Because, and I'm not going to go into a super deep dive on this, but the idea here is, and it's been a little while since I've actually read on this, so I'm not crystal clear on the theory behind it, but you can change the MAC address, and I believe there's 2 MAC addresses that are per VM when it's initially fired up, and I'm getting a little fuzzy on the details. I honestly don't remember all the specifics, but MAC address changes means is basically what I wanted to cover is traffic leaving away from the virtual machine. So anything it generates. Forward transmits is going to be traffic coming towards it, or it might be the other way around. This might be towards it. This might be from it. Transmits, yeah, send it. So, but I'm not going to get into too much more detail on that because these MAC address changes and forward transmits are turned on by default, so I don't mess with that. We have traffic shaping. Traffic shaping allows you to basically slow down the forwarding of traffic from the virtual machine as it's being sent. That's basically what it means. And so by default, it's disabled. You can enable it and then filter it down. So the idea here is if you say over a period of time, and this is usually done in 1 second intervals, and the way that shaping works is it doesn't look at it in the 1 second time frame. It basically will take that 1 second period of time, and it'll break it down into several individual time frames, which might be 100 milliseconds, which is there'll be 10 100 millisecond time intervals inside of a 1 second time frame, because there's 1,000 milliseconds for every 1 second, right? So if you break that down into 10 100 millisecond chunks, the shaper would run over that particular that time frame. So to break this down and how it actually would work, it's actually pretty simple. So the general idea here is this. This is the way that Cisco does it, and it's pretty close to the way that VMware does it too. So let's say you take, this is the hardware queue of a virtual machine's network adapter, and on the vSwitch. So we'll say this is a 1 second period of time. We're going to break this up into 4 equal sections. So each one of these sections is going to be, and part of my drawing again, I'm no artist. This is 250 milliseconds, 250 milliseconds, and you can figure out the rest, which equals 1,000 milliseconds, which equals 1 second, right? Well, in order to figure out how much data is going to be sent every quarter of a second, you have to figure out what the actual configured interface speed is. So if it's 1 gigabit per second, what that means is going to be every 250 milliseconds, you are going to send 250 megabits per second, or you're going to send 250 megabits. The reason why it's 250 megabits is because for every quarter of a second, you're going to send a quarter of the total bit rate on a per second average. So what this means is if the interface, the vSwitch is configured to send 1 gigabit per second on a per port basis, then the most you can send in a 1/4 second time frame is 250 megabits, because that's what is going to be able to be serialized from layer 2 to layer 1 every quarter of a second. If this was 10 gigabit, it'd be 2.5 gigabits per second. If this was 100 megs, it would be 250,000 kilobits per second, because of the way that it's, if 1 megabit, 100 megabits would be 25 megabits per second. So it just depends on what the configured interface speed is, divided by the amount of intervals per second that the shaper is running over. So that's the idea. So for every 250 milliseconds, you're going to send 250 megabits per second. And so what you do is, if the burst size, let's say for instance in this first interval, you can send up to 250 megabits per second every 250 milliseconds. So the idea here is if you send, say, 200 here, you send 200 here, you send 500 here, and you send 200 here, over the course of 1 second, how much is that? Well, if you take 2 and 4 is 400 megabits. You have 500, which is going to take you to 900 megabits, and you're going to have 200, which is going to take you to 1.1 gigabits per second. right? This is going to be 1.1 gigabits per second. So what's going to end up happening is you're going to have in that, for every quarter of a second that it's going to be sending traffic out, it's going to be shaping. If it doesn't reach its total capacity for that one particular interval, what will end up happening is you'll have bank, which means it'll be actually able in the next shaping interval. So if you only use this one, you have an additional 50 megabits per second that can be added to the next interval. And then what you do from there is then that puts this guy to 250. But in this case here, you're only sending 200. So what ends up happening is the third interval, you have 100. But the problem is you're trying to send twice as many as the maximum allowed. So what ends up happening is in this particular interval, you're sending more than what you could possibly actually put into this particular interval. So the idea is you've got, but a third interval, you've only used about 40% of your total capacity. So you've got 100 megabits extra that you could average in this particular interval for the shaper to run. But the problem is you're trying to send more data in this 1/4 second time frame than is totally allowed for this particular average. So what you have to do is on this particular interval, you have to shape this guy down to 250 megabits per second, which means the overflow that it's getting has to be shaped, and the stuff that's sent in before that has to get forwarded, because you can't forward the extra here and keep this guy shaped, because whatever comes before it takes precedence because of the fact that it came before it in the queue, unless you have some sort of QoS mechanism in play to where traffic in this particular interval was prioritized over traffic in this particular interval, which is totally possible. You might have voice over IP, you might have some sort of mechanism in place where you're saying web traffic is prioritized over, say, FTP. It really depends on your network specifics, but whatever traffic comes in before that is forwarded before the newer traffic is brought in. So what ends up happening is the extra 250 megabits per second that was being shipped out at this particular 1/4 second interval is shaped or slowed down. The difference between shaping and policing is shaping will try to buffer it, which means it'll try to hold it and slow it down until there's an open time frame in the same shaping interval that will be able to forward the traffic. So in this next one, we're under our total amount, which means that since there's 50 megabits extra here that's allowed to be able to be used, then we're going to be able to take 50 megabits from this range and drop it in this one. So that begs the question, what happens in the next 1 second? Well, it'll actually keep buffering it until all this data gets out. But because of the fact that it doesn't just drop it, because policing will just drop the traffic. Anything extra excess over 250 megabits per second in this 1/4 second shaping interval will get dropped. Shaping, it'll get buffered. It'll get queued. This is what they call fair queuing. So the idea here with a shaper is you take this information, you shape it. So you save it in memory, and then when there is in a 1/4 second interval, if the full queue bandwidth isn't used for that 1/4 second, anything that's extra is able to be dropped in here. So this traffic right here, this extra 250 megabits right here, this will get saved for a later point in time. And then eventually when more data comes in, it'll get sent out. But this stuff will have to wait until either there's one of these 250 millisecond shape averages isn't completely filled, so there's room to spare, or there's some sort of priority that comes into play, or there's a timeout in the application like TCP or something like that. UDP, there's really no timeouts, so if you're trying to send data, you'll get some, the data will come up kind of garbled, the picture might get a little blurry. If it's TCP connections, you might your window size might drop down a little bit because you might time out. Things like that will come into play. So it's important to understand how that breakdown works, because if you don't understand this is going to be a big problem later on if you don't get how this all breaks down. So, and then by default this is disabled, so normally we don't mess with it, but it's important to understand how that would come into play. And then NIC teaming. NIC teaming is how you're able to take multiple network adapters and utilize them for forwarding traffic. So typically, a route based off of originating virtual port ID, You can do route based off of an IP hash and source MAC hash. Use explicit failover order. There's a lot that goes into determining what happens when you do this. You have link status and beacon probing and things like that. So the way that beacon probing works means you have to have 3 or more network adapters to this. And the idea here is a beacon is sent out one interface and brought in the other 2. And if one of the beacons fails, then you would say, okay, which particular port did it fail on? That could be the fact that the network cable was unplugged. When you're doing this, you're doing explicit failover order. You specifically tell the vSwitch how you want it to fail over. So usually I don't ever mess with that. You have notify switches. Notify switches basically means that when you are setting it up, if something does happen to where if a link fails, and you learn more information in, you do what they call a gratuitous ARP. And what a gratuitous ARP basically means is you go out and you volunteer information out to the rest of the network. You say, okay guys, here's the deal. I have learned this information in. I need to flood this up to the switch, the physical switch, to update your CAM table so that you know what's going on. So if you receive traffic in from me and you don't recognize any of the MAC addresses, you don't have to sit there and ARP for it. Here's the information I've already got. Fail back means that if a link goes down, so if link 1, I'll say you have 2 network adapters. If NIC 0 goes down and you still have NIC 1, and everything fails over to, and this would mean you would need to have an adapter here in the standby adapters. If your active adapter goes down and your standby adapter goes to active, and then your active adapter that failed comes back, then you would fail back to the active adapter, or to what was originally the active adapter. Now that could cause some outage window and stuff like that. I always choose failback of no, and the reason for that is because if something does happen, you would keep the standby adapter active, and then if it failed, it would fail over to the what was originally the active adapter. So that's how I choose to do it. You can do whatever you'd like, but that's just how I go about doing it. And then we have network adapters. This is where you would add physical adapters to this network, and so you can click on add. And I have several adapters I can use in here, but none of them are really they're all down because there's no physical cable plugged into these ports. So I'm not going to be able to do anything there. But if I was to go to say edit, and I was to say auto negotiate, I could tell what the speed and duplex is and stuff like that. I go back to ports and I say I want to edit the management port group. Now what I do with this is I give it a VLAN ID of all. So I click on edit, and in here the network label, this is where the network label comes in, where it says MGMT, where I'm hovering my mouse over. That basically is where when you get that, this is the virtual machine port group. This is the label, and what you do is this network label is what next to a virtual machine's network adapter, there's going to be a drop down box, kind of like this one, and you would choose which particular network label you want it to be put in. So when you choose a network label, that's the port group you're assigning that network adapter to be in. So that's its broadcast domain. Now the VLAN ID here, we have a couple of them, and if I was to pull this guy out here, I could type in my own, but in this case I'm choosing all 4095, which means that all VLANs are going to respond to all their VLAN traffic. So basically the virtual switch turns into a localized router, if you will. So they're able to, like things like all these routers that I have over here on the left hand side, they're able to forward traffic to each other. So that's how you're able to see some of my videos where I go into some really crazy routing designs. That's how this is all taking place. And so again, we have security and stuff like that as we go along. But so if I wanted to change the VLAN, or let's say I had hundreds of VLANs, you would come in here and you would create the VLAN IDs here, and then when you would create a network label, you would associate a VLAN ID to that, and then that's where this would get play. So down here I created VLAN 12 is set up as such, and it's got a VLAN ID of 12. So when it leaves out here and goes out to the rest of the network, it's got the association of VLAN ID 12. That only affects traffic that is going to be going out of the network. So If you want to completely separate your traffic, let's say you want two different VMs to be talking to each other and only each other, you would create, but not to the outside world, you would create a vSwitch, what they call an internal only switch. The internal only switch basically means that there's no physical adapter. So when these ASA to AT to R2, what this basically means in router 2 is this ASA virtual machine interface and this router 2 virtual machine interface. Well, actually, there's only one in there because this is the port group name, ASA AT2 to R2. This guy right here is the port group name. This is the virtual machine that's in that port group. And here we have ASA1 or ASA1 to DMZ1. So we have DMZ1 and ASA V95 1-1. So these two particular VM port network adapters can talk to each other. So if DMZ1 is 10.1.1.1 and this guy's 10.1.1.2, they'll be able to ping each other because they're in the same virtual switch. So that's how I have it set up here for just a lot of my labbing. So that comes into how that would come out to play. So pretty straightforward stuff when you think about it. So, and there's the nice thing about it is when you have a vSwitch configured. So let's say, for instance, you want to set this up. You click on Properties here. Right now, I only have one particular VM kernel adapter. A VM kernel adapter simply means this is a layer 3 management address. So if you want to remote into the network or what have you, or be able to ping it, this is where you would do that. This is where you would also set up whether it's going to be vMotion, management traffic, fault tolerance logging, things like that. You would also be able to create the IP settings. This is where I went through and no IPv6. I would actually have to reboot the host in order to disable this, but this gives me the ability to come in here and play with different capabilities and stuff like that. So the port group, you can have, let's say for instance you have just one vSwitch. So you have a physical port, one physical cable plugged into your ESXi host. And then you want to be able to run all of your traffic over that. Totally doable. So what you would do here in this case, I'll grab my pencil real quick. So you have this situation like this, where you have one vSwitch. You have a VM NIC adapter, so VM NIC 0, and this guy connects down to a switch of some sort, whatever it might be. What ends up happening here is you have vSwitch 0, so I'm just going to say this is vSwitch 0. What you would do here is you would create a port group and a VM kernel adapter. So I'll just draw a line for a VM kernel adapter. Then you do a port group and a VM kernel adapter. And just repeat the process over and over again. Now the idea here is that you would associate a VLAN ID. So you have a vid here, a vid here, a vid here, and a vid here. By doing this, when the traffic leaves the port group and hits the interface, whatever port group it came out of automatically gets that tag of 10, 20, 30, 40, or what have you. And then this could be management. This could be, vMotion. This guy could be SAN. This guy could be production. And by doing this, let's assume this is a 40 gig connection, 40 gigabits per second. So by doing this here, when management traffic comes out here as VLAN 10, everything goes across this wire, but as it goes in here, it's placed into different VLANs. So we have 10, 20, 30, and 40. And as traffic comes out, it gets placed in the correct VLAN as it goes. So you can do this on a per vSwitch basis, because there's been times where I walk into customer networks and they only have one physical cable plugged into the network. So they have a cable running from a switch to their ESXi host. It's one cable. And I look at them and I go, that's it? That's all you got going on here? And they go, yep. I'm like, okay, no problem. We can do that. And then I had to go in there and I had to do the VLAN tagging. This is no different than a Cisco switch, like what I have in my personal network here, where I have in a test environment, I have 30 VLANs. And by doing this, I am able to connect out to a couple of other switches that are in my network that go off to different things. My 3550, it has the EMI image, which allows me to do layer 3 routing. So what that allows me to do is the vSwitch acts as a flat layer 2 network. So you have your port groups act as VLAN, a place for you to put ports into different VLANs. So port group just equals VLAN at the end of the day. So if there's no VLAN ID associated to it, if it's VLAN ID 0, it's in VLAN 1 or the native VLAN. Whatever the native VLAN is configured up here is where that port's going to get placed. So if your native VLAN is 0, if native VLAN is 0, it's tagged as 0 equals to VLAN 50, then that's what VLAN that anything that's not manually tagged with the VLAN is going to get put into when it gets a switch. Simple as that. So that's the general idea of how that would work. So that's the basic breakdown to how this would all come into play and how it all works out. I hope this has been informative for you. I'd like to thank you for viewing.